somewhat disastrous statistical lecture where I got your levels completely wrong, for which I apologise. Other of you, it's the first time you've endured my lecturing. I'm here to talk about databases, which I'm trying and falsely convince you the plural is data bar. It's that, radius, database, data bar. I'm wanting to get that into the American language. I think it's funny. You've got me for 3 weeks, or 3 lectures, and this is what I'm hoping the outline is going to be. So today is going to be some database theory. Now, how many of you have studied databases before? Can you put your hands up if you have studied databases before? What sort of database?
Relational.
Yeah. And what environment?
Oracle. Windows.
Okay, so this will be basic for you, but that's great. Anyone else?
I did a little bit Microsoft Access.
Okay. Yeah. Microsoft Access is a very intriguing package. MySQL is a lot less friendly, but a lot more powerful, which is going to be interesting. Okay, so good. The main thing is I'm not going to do what I did the previous lecture, where I taught basic stats to people who had all PhD epidemiologists. I felt a complete prune when I finished that lecture. I'm sure you thought, God, how many times has he messed it up? So, first of all, I'm going to talk a little bit about database theory. And the main outcome here is to understand database normalization. Next week, or Thursday, is going to be a very much practical lecture. And I'm going to talk a little bit about SQL Server, or SQL, and how to do it. And then there's going to be lots of exercises on SQL. Hands up who's used SQL before. So a few of you, okay. This is going to, what species of SQL did you use?
It was back in college.
It was back in college,
I
yeah.
remember.
No, don't worry. So hopefully it might be a refresher anyway.
Yeah, sure.
And you, sir?
Postgres.
Postgres, yeah. I'm actually going with MySQL. The advantage is they're both ANSI standard SQLs. If you've done Microsoft SQL Server, Microsoft being Microsoft says, why bother with international standards? Let's come up with our own one, okay? And finally, on Tuesday the 21st of November, I'm going to talk about linking R and SQL. The key outcome for that is you are able to call SQL from R, and there will be a little bit of statistical modelling based on the result of that data. Just a hands up, because I'm trying to work out what lovely exercise to give you. Hands up who had done negative binomial regression. Okay. I will slightly simplify the exercise, but that's fine. I mean, the purpose will be the same. Okay, right. Well, shall we kick off? First of all, one of the things we're trying to achieve before I start on this, I'm just going to talk about R. R is fantastic, beautiful language. Everyone should be using R for almost anything. One of the problems, though, is it doesn't handle very, very large data sets particularly well. So, certainly until quite recently, no single R object on a Windows, for those unfortunate people who use PCs, sorry about that, could actually be more than 2.5 gigabytes big. Even if you had like 100 terabytes of RAM, no single object could be more than that size. This creates all sorts of issues. Now, there are ways around that. One of the ways you can deal with that is to actually use a database to store your actual data. There are other things which we might touch on the third lecture if we get that far. The other issue is timing. So in the UK, I used to do a lot of work on UK claims data. And there were about 1 billion claims records, which came in all sorts of different ways. And we used to try and manage them with SAS. Any of you SAS users, by the way? Great. So we used to try and manage them with SAS. And basically, a process when we were trying to link files together took about 24 hours. On Microsoft SQL, it took about 5 seconds. So hopefully, what this can do is be a lot quicker than actually using, the overhead of mixing data between R and SQL will actually give you a certain amount of advantage. I mean, there are various bits of database theory that I'm going through. Can I just check? We are intending to finish at 2:30 today. Is Is that correct? So you've got me for an hour and a half, you all unfortunate people. Okay. So, one of the things we talk about in database theory is ACID. And basically, one of the key things is where databases work particularly well is where you've got lots and lots of people trying to put stuff onto a database and with lots and lots of conflicting things. So if you have a bank, you might be taking money out or putting money in while somebody else is taking money out, paying bills, etc. So one of the key points about relational databases is to deliver something called ACID. So first of all, the ACID, the atomicity, is the transaction either works or it doesn't work. Yeah, there is no halfway house. The other point of things is we actually, everyone sees the same state of data, which is quite hard to do, and translations are isolated from the other. So it should be relatively unimportant whether this transaction happens first or this transaction happens first. And finally, durability. So when you pay money into your account, it stays in until you take it out. All highly desirable properties. Anyone work with NoSQL databases here? No? Okay, no reason why you should. They are fantastic. They are perhaps the future, and they sacrifice some of these restrictions in order to get much, much higher performance. But I will not talk about them then. Good, that's always fun. So, kicking off then, analysis and modelling of data. This section explains the role of conceptual data modelling in the overall analysis and design of information systems. Now, one of the things is I started my life as a mathematician, then became a statistician, and I started working with very, very large data sets. One of the problems is we as statisticians are absolutely appalling at designing data structures for very large data sets. And so the idea of this session is to give you some idea of best practice with designing databases. But as I said, the next two lectures are going to be very practical. So, we start off with something called, by the way, were you all able to download these slides? No? Yes? Good. Okay, conceptual data model. And this is a detailed model that captures the overall structure and data in the organisation. So before we actually start messing around with actual individual databases, one of our first jobs is to try and actually capture the relationship between the data so we can plan the data. I'm going to look and see what you're laughing at. Okay. I thought you would say, no, he's made a terrible mistake. But anyway, so we will carry on. So we'll talk initially about this. Okay. So one of the key issues is something called an entity relationship diagram that actually models how entities relate together. So I'm doing a huge project with some people from Pop Health looking at Chipotle, food company. And we have a copy of every single of their relational database. Okay? We have every single transaction that they have ever done, we have sitting on a server. And there's a really poor, unfortunate PhD student who has a nightmare job of trying to load this. Now, Chipotle, as a bit of a company, a fast food company who also operate in New York, I shouldn't really name them, forgot to give us the entity relationship diagram of their data. So all we've got is these hundreds of tables of data, and we've got to work out how they fit together. So if you are connecting to a database, one of the things you should be asking for is something called the entity relationship diagram. Okay, quick stop. Is this roughly what you were expecting? Yeah? Is this patronisingly simple? Okay, great. So an entity relationship diagram gives you a collection of how things fit together, etc. And it's a really, really key tool in actually analysing your data. I shouldn't walk around so much. So here's an example of a conceptual data model. So what do we see here? We have a supplier, okay? It's a box, yeah? It's an entity. And a supplier makes shipments. A supplier has many, many items that they do that. And that says basically one supplier can supply many, many items, and an item can be supplied by many, many suppliers. Makes sense? We have customers. A customer submits an order. Now, these two lines here, and we'll go through the relationship a little bit more, says that one order can only be for an order can only be for one customer. Makes sense so far? Yeah. But one customer might submit many orders. Yeah? Isn't this exciting, guys? Come on. It is exciting. Okay. And one order will be of many products. Okay. And one product might be supplied in many orders as an item. So this will say 15 of, left-handed corkscrews for this particular item. Now, the key point about this entity relationship diagram is it tells you the relationship between the different data in the table. Okay, so if you actually work with a database, it's really important to have a diagram that looks a little bit like this. Okay, this slide isn't in your deck. The next slide isn't in your deck, but here's an example of a healthcare-related one. So what do we see? Can you read this, by the way? So we have a patient, okay? And a patient has all sorts of attributes about them. And a patient, because this is America, not England, sorry, I'm English, we have free healthcare, but I'm not going to rub that in at all. A patient has a number of different payment methods, yeah? The little form things here. A patient will have an address, that's quite useful. A staff member will have an address. And a patient will interact with a member of staff by a patient record. Okay? So one of the things you may find yourself doing is trying to actually extract data directly from a database. So a lot of my work, we're actually pulling data from underlying Epic, and we need a data structure that looks a little bit like this. And so you can do this. So you can actually write queries that can pull data directly from the Epic electronic health record and makes your life so much easier. Okay, and I understand you're smiling. This is exciting stuff, guys. This can revolutionize your life. Okay. So, some more definitions. An entity is a person, place, or object, or even a concept in the environment. An entity type is a collection of entities that share common properties and characteristics. And an entity instance is a single occurrence of that particular entity. So presumably, all of you are of the entity type student here. Yeah, you are an individual instance of the entity type of students. It's a wonderful language, this, isn't it? It's great. And we then get on to the UML modeling language itself. Or we can talk about how they fit together in the internet relationship. And people differentiate between the data model, which is a hugely detailed thing, which will give you detailed examples of exactly how the data is, and the pretty picture, which is the entity relationship diagram. If you're bored, Google NHS Data Dictionary, and you will see that the NHS Data Dictionary publishes for every single healthcare thing a very, very detailed data model. So it will tell you if you have an outpatient appointment, this is the data that we expect you to store about it. This is the format of how we store dates. This is how we store NHS numbers, etc., etc. Okay. Questions so far? There will be questions for you later. Okay. So, I'm going to skip over this slide really, but to say a lot of the work in data analysis is to try and understand the object and their data entities and their descriptions, and come on to something called a primary key, which which we're going to discuss shortly. So, I mean, I'm bored with this slide. I'm going to go over this one, go to the next one. Okay. So, or not. So now this one's boring as well. I'm going to go straight on to this one, which it actually shows you the building blocks of a entity. So classically, boxes are entities. Lines show relationships. Mandatory ones, double dots. Mandatory many, single one of those. Optional one, little o. Optional many. And you can have trinary. How do you pronounce that? How? Yeah, I pronounced it incorrectly, but thank you. This is how this lady pronounced it. So let's go into some more examples of these particular things. And this is a modelling notation called Universal Modelling Language, UML. Any of you use that? No? Yes, somehow I guessed you might have done. Okay. I'm not going to be particularly heavy on this, but so when you actually have an entity, you should give it a name. And the convention databases people have is it should be a singular noun. So it should be student, not students. It should be descriptive to the organisation and concise. So again, and it's the result of the event, so it's not enrolment, it's the fact that you're a student that's the important issue here. Okay. And classically, you should have in a data definition, you should include a statement about what is unique about it, and I mean, if you have a look at the NHS data dictionary, you will be able to see an example of, for every single entity, permitted values, how you audit it, how the data is collected, where is it derived, or is it actually entered on a system. So entities have attributes. So a classic attribute might be, for you as students, might be your name. It might be your grades. It might be the course that you're attending, etc. And the classic thing is in an entity relation diagram, they are placed inside the box. Right. Noun and unique, have we done that one? I think we must have done. Okay. I mean, and again, have a look at the NHS data dictionary for an extremely verbose example of how data dictionaries can be constructed. One of the important things, again, is people forget, in healthcare, we tend to have lots and lots of names for the same thing. Is that true? Okay. How many of you are physicians here? No? How many of you are other healthcare practitioners? No. How many of you worked in a hospital? Okay. And how many of you are biologists? Okay, right. So again, we need to have great fun defining exactly what we need to do, the source and value of attributes, aliases, etc. One of the great things about healthcare is everything has half a dozen different names, whether they're physicians might be providers, they might be physicians, they might be doctors, they might have all sorts of other names. Okay. You should actually specify explicitly if an attribute is required or is it optional. So for instance, presumably, if you have a name, if you have a student record, the name might be required, for instance. Their social security number might be optional. And so we need to specify in a huge amount of detail what is required and what is optional. So we now get to the exciting issue of how do we actually identify a student. And classically, what we want to do is for any sort of identifier, we'll have something called a candidate key, which is something we might be able to use to identify an individual student. So students, presumably you have student numbers at NYU? Yeah. So that might be, that is a candidate key. Your name is also a candidate key. So why might we prefer your student ID as your identifier to your name? Go for it. Yes, I mean, yeah, there is no standard. You know, people will actually change the way they do names. Certain ethnic origins put names in different formats. People spell names differently. A lot of my friends are Irish, so O'Hara is sometimes O'Hara, that's one word. O apostrophe Hara, which makes a nightmare for SQL, which we can come on to later. And so yeah, you're right. I mean, you know, standardised names. People misspell names. People change their names. So names tend not to be a particularly good candidate key. Unique identifier. So when we actually have a candidate key, we want to choose a candidate key that will not change its value. That will never be null, so it will always be present. We tend to avoid using, when I say intelligent keys, keys that actually give away information about what the record is. And I'll give you a classic example from the NHS. So in the NHS, we have a unique identifier called the NHS number. Yep, sounds reasonable, like your social security number. Some idiot devised a system where each record actually was linked by the person's NHS number and a count of how many, say, referrals they had. Now, like your social security numbers, our NHS numbers uniquely identify a patient. So this candidate key, this key, could enable you to actually identify the patient who was of interest. So it's a very bad idea. And sometimes we might put 2 or 3 numbers together. So here's a question for you. Is vehicle number plate, does number plate translate? Do you say license plate here? Yes. Sorry, forgive me, it's British English, okay? Does vehicle license plate, is that a good identifier for a car, given those rules? Okay, why? So one of the questions I would ask, does a number plate ever change? Yes, it does. Yeah, so you can move your car around. And in fact, and if you move state, you would change your number plate. Is that right? Yeah. So license plate number. Sorry, number plate in English. License plate number in American English isn't a good candidate number. I mean, in practice, another thing is, and this is going to be uniquely English, but I can share it with you everywhere. Not every car in England has a number plate. The Queen, for instance, she has her Rolls Royce, does not have a number plate. So we couldn't use a number plate here as a number. In practice, all cars, and if any of you are petrol heads, I apologise if I get this wrong, have something called a VIN number, or vehicle identification number. And that I do know happens in the US, and that is unique. It's stamped onto the vehicle chassis, and its stamp tends to be all over the car in various places in case the car gets stolen. Okay, so one of the things is to think about something that is never null and never changes. So you're not clinicians, but is the New York State license number a good identifier for a nurse? No, good question. Why?
Change her car license plate.
Yeah, sorry, no, in fact, here I mean her state registration number, sorry. And again, this is British English, slap hand, I apologise, but so, when you register as a nurse, it's you get a unique identifier. I don't, as that. But you're right, it's not. Go on, you had a point?
No, I didn't have one. What do you mean, New York State license?
So if you are a nurse in New York,
Okay, I got it.
you get issued what's called a New York State license number when you practice.
Well, while she's in New York, maybe it's legit, but when she goes to New Jersey or Connecticut, it's
So every time she moves states, her license number will change. Yeah. So we do have problems actually finding out decent candidate keys. And another example from the UK, I apologise for all these, I am what's called fresh off the boat, okay? I know some of you also are fresh off the boat, but I am very fresh off the boat. So another example from the UK. So one of my previous jobs was to work out how many of the different types of physicians we needed in the UK. So how many, how many surgeons we might need in 20 years hence, how many psychiatrists. Okay. So we had a database which we collected details of every single physician in the United Kingdom and of every single dentist. Okay, and that's fine. We thought, okay, we'll use what's called their General Medical Council number. Now that's fantastic because that never changes, okay? And it's right the way across everyone in the UK. And if you practice in the UK, you have to have one by law. So it's perfect in so many ways. Then we discovered that actually dentists don't have General Medical Council numbers. They have General Dental Council numbers. Okay, so we can have your General Medical Council number or your General Dental Council number. And that was fine. And then we discovered there was another group of people who are called Associate Specialists in Public Health. And they do a special training. They are people like yourself who have got an advanced degree in something relevant and can train to be a public health physician. Of course, they're not medical doctors, so they don't have General Medical Council numbers. So we then had to invent another set of number for this. So the point about this is identifying, primary keys can be quite challenging. The key point is it should never change its value and it should never be null. In the UK, as I said, we can use NHS number. In the US, Social Security number is excellent, but it has two problems. First of all, many people will not want to devise their Social Security number for quite legitimate reasons. And secondly, does anyone know a problem with Social Security numbers for people over 80? Women over 80 specifically. I only just discovered this recently when we were doing some work on Medicare data. And when Social Security numbers first came out, women were given their husband's Social Security number. So this will only happen for people who, I think it's over 85, but this is a very, very rare case. But actually, I couldn't understand why this person was both male and female. And I was sort of explaining this to the person. I said, no, you're an idiot, because Social Security numbers pre-19, whatever it is, were not unique for women, because women were treated under their husband's Social Security number. So actually, when you're choosing a database, actually trying to understand these numbers is a real problem. Okay? Right. How are we doing time-wise? Oh, gosh. Doesn't time fly when you enjoy yourself? Okay. So a relationship is an association between the instance of one or more entities that is of interest to the organisation. The degree is the number of entity types that participate in the relationship. So here we have an interesting type. We have a patient, and patients might have two subtypes. We might have an outpatient, and they have a check-back date, and they might have other data. And we might have a resident patient, I would say inpatient. Do you say inpatient here? Okay, inpatient, and they might have a bed ID. Interesting, this slide is interesting because this implies a resident will only have one bed, but in practice, the patient might move beds, so this is not a very good data model. But all patients have a responsible physician. Make sense? And one of the things you'll often find is when you look at databases, you will say that actually this is not right. They have not correctly modelled the part of the environment, and it is extraordinarily difficult to try and do that properly. Specialisations. I'm just going of subtypes. And basically, I'm just going to go straight on rather than read this to give you some examples because it's more fun. Disjoint and overlapping rules. So, for instance, in our patient example, a patient might at different times be an outpatient and a resident patient. Or it may be at any one time they can only be one of those types. So, if we have a look at here, this is another way of representing the data. So here is a university system, and we have the concept of person, which has social security number as a unique identifier. Okay? It's persistent, it's never null, and hopefully we can persuade as an employer people to do that. Did you have to divulge your social security numbers as students here? Yeah, okay. Name, address, gender, date of birth. Okay? And they can be one of three types. They can be an employee, an alumnus, or a student. Now, the O says that we could have somebody who is both an employee, an alumnus, and a student. So at one point in my life, when I was at London School of Economics, I was both an employee, an alumnus, and a student, all simultaneously. Okay, so this is possible. On the other hand, an employee, we have what's called disjoint employee. They can either be a faculty member or they can be a member of staff. So they cannot be both at the same time. And again, a student can either be a graduate student or they can be an undergraduate student. They cannot be both of those simultaneously. Happy so far? They can't be both of those simultaneously. We hope all of you, after you love your undergraduate, I know you're doing postgraduate degrees, that you want to stay on and do a graduate degree with us afterwards. But at one point, you have to be one or the other. Yeah. And we have a relationship between entities called the associative entity. This is something that links one entity to another entity. And for reasons I can never understand, having once studied grammar, I don't know why you would call that as a gerund, which is a verb used as a noun, like skiing. But people tend to use this phrase for this. So let's give you some examples of this. And then I'm going to give you a tiny break while I ask you some questions. So, an employee might be on a course. And the associative entity here is the date they completed. It might be the date they started, but you can see that you're there. An employee might be on a course, and the associative entity might be their certificate number. Again, an employee might be on a course, and perhaps better still, we should have certificate number and date completed. And we have chosen to say certificate number underlined is the primary key. Right, to give you a tiny break from this exciting stuff, I'm going to ask you some questions. So hands up who are PC users here. Okay, you're a minority. How many Apple users? Okay, and how many Unix or Ubuntu or anything like that? Few. That makes my life a lot easier. So one of my problems for next week is the way that you get SQL and R to talk to each other is completely different depending on if you're on a PC or a Mac. And so I am going to have to try and do both simultaneously. If I'm a Mac user, and if I fail on that, please tell me, and I will try and make sure that we actually do this. So, but unfortunately, I do not have a PC I can test this on, but we shall have a go for that. Okay, that's useful. Okay, back to the exciting stuff here. Okay, and this is going to... So, I mean, again, the purpose of the entity relationship diagram is to capture the richest possible understanding of the meaning of the data necessary for an information system and organisation. So when we got the data from Chipotle, the fact that we did not have this data, we have had to spend hours, well, literally days, trying to reverse engineer the entity relation diagram from this data has been an absolute nightmare. So it's really important that you actually get them. And if ever you have to connect to data, it is very legitimate to ask for the entity relationship diagram. So this slide is slightly out of sync. We talked about people in an organisation either being a student, a staff, or a staff member. and we talked about staff members having subtype faculty or staff. And so a subtype is going down, a supertype is going up. That's lovely. Right, what should we talk about next? I think fields. So fields are the smallest unit of meaningful data to be stored in a database. It is the physical implementation of a data attribute, and we tend to give them wickedly sounding names. Some very special fields. We talk about a primary key, which is uniquely identifies a record, and a secondary key, which I'm going to gloss over until we do normalization, and the rest of these I'm going to talk about when we actually start about normalization shortly. But there are their formal definitions. Okay. So we talk about a record is a collection of fields arranged in a predetermined format. They classically, in most SQL databases, have a fixed length, although there are ways that you can do variable length, but things just become much harder for that. Blocking factor is to do with physical structure of databases. I'm not going to do that. If you have to actually understand things like blocking factors, my suggestion is you talk to a database administrator, but we can catch that in the practical things. A file is a set of all occurrence of a given record structure, and a table is the relational database equivalent of a file. And there are all sorts of lovely types of things we talk about. A master file records relatively permanent data through though they may change with files. So a classic example of a master file might be the list of physicians at NYU Health. For instance, so this was a file that says Fred Bloggs was employed as a general and internal medicine specialist at such and such, and this is his license number. Transaction files tend to be updated frequently, and then you can have all sorts of clever ways of actually documenting files and logging points, etc. So, I mean, again, one of the things, say, with an electronic health record, you want to log in some detail who actually accessed each and every instance of a file, in case you want to audit if somebody has accessed something they should not have done. And one of the really interesting jobs in database theory is what's called data architectures. And these are the people who actually design how the files and databases are stored, the input and output technology, etc. And these guys, classically, you'll pay about $900 to $1,000 a day to hire if you find yourself designing databases. It is an excellent career opportunity, although presumably not one that you're interested in, doing the research degrees that you are doing. Okay. There are different types of ways that we might use a database. And these might affect our database. I'm going to focus on two different types. One is an operational database, which is designed to support day-to-day transactions of your business. So this will be a database that will record every single, say, deposit, whatever, that you put in your bank, or every single patient record. And this is designed to be as efficient as possible that clinicians or bank managers or whatever else can actually access the data on an operational side. The second one is a data warehouse, which is designed for people to actually access data to write very complex queries on. Now the point is, the two of these have different requirements. Here it's about logging complex data, and meaning you can access an individual record very, very quickly. Here it's people who are going to probably access many, many thousands of records and access, and make summary information for them as much as possible. And you can have all sorts of other ones, which I'm going to gloss over. Right. And so, you classically go from a logical model where you say have a customer, an order, a product order, and a product, to actually the physical data structure that might look like this. Sorry, can you see this? That basically the physical model says that we've got a customer table, they've got orders, they've got products, and there's a product table. So we go from the logical structure to this is physically how you might build it in Access or MySQL or whatever other database. So, carrying on, it's an exciting theme. Good data models, simple, and she'll try and highlight redundancies. The goals are achieved through database normalization, and this is what we're coming on to, which is the really exciting and the most important part of this lecture. So we're wanting to design data that is good for efficient storage, reliable, and adaptable. Now, one of the fascinating things is data structures of organisations change remarkably slowly. And I remember doing some work for a social services department in Kent. And I went back 10 years later, and their actual physical data structure hardly changed at all, though their processes did. So one of the things that's fascinating about data models is they tend to be remarkably persistent over time. Anyway, schemas. Right, let's go on to this. Okay, primary key attribute. We've talked about these a bit at all. They're often called a criteria. Some quick refresher: should never change its value, not null, avoid intelligent keys, and we sometimes may be combining things together. We'll come on to that shortly. These slides have changed their order. It's very annoying. Database normalization. Okay, so this is perhaps the single most important bit of this lecture. So one of the key points about database normalization is to eliminate redundancy, organize data effectively, and reduce the potential demand for anomalies. And we'll come on to these in rather more detail. So this is the key actual bits for the lecture, the next bit. Okay. So we talk about different types of anomalies, updating anomalies, insertion and deletion anomalies. Now, I'm going to say this a couple of times, but I'm going to do an example on the board, okay? Now, I am illiterate, so my spelling is going to be really bad, okay? And you can just laugh at me for my appalling spelling, okay? But suppose we have a database, and we have student name, okay, and we have student number or social security number, and we have tutor. Okay, does tutor translate? You know, do you have a tutor here? And we have tutor room number. Yep. Okay. So we have Fred, who has a social security number 1, because they're very old, and their tutor is Dr. X. Okay, and his room is 7555. Happy so far? And we have Harry, and his social security number is 2. Isn't that incredible? 2 social security numbers. And his tutor number is Dr. X, which also has the room 755. Now, I could go on and on and on here, but the point is we have some redundancy in this information. So one of the points is that when we insert a student here, if we insert Sarah in here, who has a social security number of 3, and she also has Dr. X. Yeah. But some idiot might type the room 745 instead of 755. So we've got inconsistent number data on our database. And the reason is that this bit here is actually redundant. So we're repeating the same information again and again and again across the boards. Now, when you're analysing data in R, that might not be avoidable. But when you're storing data in the database, the key point is to say that when we have Dr. X, we always have the same room number. Equally, if we delete all our students, because it's the end of the year, no right, no clear, somebody exists, we lose the information that Dr. X's room number is 755. So we have different, so by storing data in an inefficient way, we can lead ourselves to all sorts of problems. Okay, so that is the problem that we're trying to address. And the way, oh, there is a pin. The way we do this is via normalization. Have you done third normal form and first normal? Yeah, I thought you had. Okay. So, our first concept is first normal form. And this value in each column of the table are atomic. So you have no column with multiple attributes. And equally, you have no repeating groups. So what do I mean by a repeating group? Well, I might have, say, tutor, overall tutor, and I might have maths tutor, and I might have stats tutor. Okay, so basically you can see I've got three different types of tutor. So to be in first normal form, we must have everything with a unique value, and we mustn't have repeating groups. So let's go and see that in a bit more detail. And there you are, there's a picture of an orangutan, because why not? So here's a database, and you might well see data here. So here we've got students, we've got a student number, we've got a tutor ID, we've got the tutor name, the tutor room, and their class list. Now, one of the reasons this breaks first normal form is this particular class list. We've got two different classes here, yeah? We've got one class and another class. So we have violated the atomicity requirement of the first normal form. So one of the things, so to convert this to first normal form, the first thing we've got to do is actually, instead of having it as in this format, where we have a field with multiple rows, we put it into multiple columns. Make sense? So student 123, tutor ID James, tutor ID name 102.8, and we create another row with 104.9. Make sense so far? Yeah? You're going to be having to do this a lot shortly, okay, between now and the end of the lecture. So please, whenever I'm talking rubbish, please tell me. Okay, so this is the first normal form. And this is the first stage in trying to get data into a normalized format. I'm going to introduce another concept, which is called functional dependence. So would you agree that if you knew the tutor ID, you know the tutor name, yeah? And if you know the tutor ID, presumably you know the tutor room, okay? So we have a concept called functional dependence. So the next stage we're going to try and do is get rid of some of these problems. So second normal form, and here is a picture of a typical English person. That's a joke. Which says it must be in the first normal form, and it must be redundant data across multiple rows of tables must be moved to a separate table. The resulting table must be related to each other with a foreign key. And basically everything must be dependent upon the primary key. So let's have a look at that. So we can see that we have student ID and we are going to take class. Now I'm glossing over the difference second and third slightly here, but we are going to take student, we're going to create another table, and that's going to contain student ID and their class ID. Okay, so we've got one table, one row per student, and each student ID says, so student 123 attends this class. We have a student 123, and they also stay in this class. So we split our database into two different fields, two files even. Does that make sense? Okay, we've still got some way to go. And one of the issues that you can also see as problematic, so we've got rid of, so instead of having multiple rows for the same student, we now just have one row for the same student. That's an improvement. But we've actually, we still got something to go to get it into third normal form, because obviously tutor name is dependent upon tutor ID. And so we don't need to store that. So there's a little bit more to go. So let's go on to the next third normal form. And to be in third normal form, data must be in second normal form, And we must eliminate fields that do not depend upon the primary key, i.e. tutor name depends on tutor ID and not upon the tutor. So, let's have a go. So here, our third normal form database, we have split our database into 3 tables. So table 1 just contains student and the student ID. Table 2 says yes, student ID and the class ID. And the table 3, tutor table, contains 1238 James 555. Now, the advantage of this, of course, is several-fold. The first is every student will know that James is in room 555. Secondly, if Langone or NYU is anything like any other university, people move offices all the time, okay? I've moved offices twice in my couple of months here. And if we hadn't done this, we would have to go into every single student record and move my room number. So you can see that this, this means we need to update the actual data only once, and we guarantee it's always consistent. So this is one of the huge advantages of third normal form, is you minimise the amount of update and you guarantee that it is consistently recorded across all sorts of people. So, just out of curiosity, whenever people design databases, they always get things wrong, okay? So if this was a genuine higher education information system, what else should we be storing here? Student name would be pretty good, their address, things like that. Tutor, what else should we be storing here? Last name of the student? Yeah.
I mean, the last name of the tutor.
The last name of the tutor, yes?
The students that they do, I guess not.
No, well the thing is we can get that because this table, so we can go from 1238 and we can pull out all their
But
students.
they have multiple?
Yes, they could, but so we'll have student 456 and we'll have that little thing. So, but no, that's a really good point. I mean, other things is, do you change your tutor ever?
What do you mean by tutor?
Okay, so this may be a uniquely British concept, okay? So I'm sorry, I am fresh off the boat, and I apologise for that. In a British university, you have one tutor who stays with you for most of your career, and they are your career navigator and help you through things. So for instance, if you're at Oxford University, you have your lectures, and you have one-to-ones with an individual tutor. Do you not have that here?
I'm an advisor.
An advisor.
It's not.
But we don't
like
have one advisor that stays.
Okay, right. Forgive my. This is a transatlantic thing, but okay. Let us instead of tutor say. So in other words, if this is teacher or whatever, you would have instructor or whatever. You'd have both that wonderful gentleman and me as instructors on this course, wouldn't you? So you would probably have other things about the course they taught, when they started, and things like that. This is fascinating, and thank you very much. And if I say any British things, do please correct me, because it is really entertaining, because my wife came over, so I married an American. She gave a lecture in the UK, and she used a phrase which is the disabled, which is absolutely, sorry, I've told some of you this before, which is absolutely forbidden in the UK. It's about the most offensive things you possibly could say. You should always say people with disabilities. And, there was a sort of general tut from her audience. She said, what? And yet there are other things that we might say in England, which quite rightly, that you would be very rightly to say, actually, Simon, I don't think you should have said that. There is a particular English way for asking for a cigarette, which just would not go down well. You know what I'm saying here. For that. Okay. So, I mean, the classic thing is, so here is a representation of the diagram, and you can see that one student, actually, is that the right way around? This is the wrong way around, isn't it? One tutor might have many students, and one student might be registered for many, many classes. But here I have a fundamental problem, because one student might have, they might have many teachers for different subjects, but one teacher will have many students as well. So one of the things is that here is a mistake I've made in our graph. It was purely to see if you spotted it. That was the only reason it was there. And you all failed. It's not one of you said, Simon, you're wrong, okay? So an exercise for you. Have a go putting this in third normal form. So we can do this a couple of ways. You can watch me humiliate myself by writing up on this whiteboard, but the point is you've got to drive this, okay? So here is my classic student database, okay? How many tables do you think we're going to end up with? 2. Okay, we'll see how long that's going to be. So first of all, this is a really simple table, okay? So we've got student, their address 1, their address 2, their city, their state, their zip code, their mobile phone, their sponsor name, their sponsor contact, their sponsor, and whether they're a US or a non-US student. Sorry, this was an English example, and it was EU, non-EU student, which, so in the EU, if you're an EU citizen, you pay a tenth what you pay if you're from anywhere else in the world. It's so unfair, but anyway, it's a good thing. Okay, so that's a huge point. So we want to put this in third normal form. Okay, so I haven't put student name there, which I probably should have done. That's certainly missing. So I'm going to start off with a table, and let's try and go straight to third normal form here. Okay, so student ID, and if I misspell anything, you're entitled to completely ignore the fact that I do out of courtesy, okay? And I'm going to put student first name and student last name. Okay. Now, address line 1, does that go in this table? Okay. So, certainly current address might go in there, but okay, let's put address line 1 here, okay? What about address line 2? Yeah? Happy with that one in here? Sorry, that's meant to be deep. Address line 2. City? Yes.
What happens if there are 2 students staying in the same house? Wouldn't you separate the address out then?
Well, that's what I'm coming to. And so one of the points is, and what happens if a student moves?
Yeah.
Might you need to record? And so you've hit what I was going to design this and then make it fail, and you've hit on 2 particular problems. So one thing is, we might want to actually separate out address and actually record start date and end date and an address. Yeah. So this is the sort of real-time considerations you have when you're designing databases. Hopefully this is a practical thing. So, I'm sorry, I've forgotten your name.
Mark.
Mark. So Mark is absolutely right. So let us take address and put it into another table. Yeah. So I'm going to call this address. Okay, and file. Okay. Right. Okay. So presumably this is going to have the student ID. And the start date in that address. And the end date in that address. Seem sensible so far? Yeah. So here we can have one student can have many addresses. Okay? Every student needs at least one address, presumably, so we can't contact them. Okay, what else might I put in here? So address line 1. Yeah. Yeah. What? Go on. Somebody shout out another one. Okay. Right. So that's an interesting point.
I don't know. Addresses consisted of like street,
Yeah.
city.
But here's an interesting problem. Do you remember we talked about if something's functionally dependent on something else, then we should put it into a separate table. If you know the zip code, do you know the state?
Yes.
If you know the zip code, do you know the city? So in fact, what we probably should do, address 2 and zip code. Yeah? So I have to be careful because I know a lot about UK postcodes and I suddenly will say something about US zip codes. And say, well, actually, there's a country example. There's one zip code which might be across 2 states. I don't know of that, but who knows? And one of the nightmares for a database design is you start doing this sort of design, and then you suddenly realise that what you actually did was completely, just didn't make sense logically. So okay, so we'll put address line 1, and we'll create another table called zip code. Yep. Primary key, zip code. Okay, not best practice, but I'm going to do it. And state and address. State and city. Now, interesting thing, again, do all US addresses follow this format? So, I don't know, but my father's address is Badminton House, Badminton, Dorset. It has no road, it has no street, okay? And it has a, there are unique UK addresses which don't follow this particular thing. They're comparatively rare, but you might get. So one of the nightmares of designing databases is to try and think of all the exceptional cases for this, where people, won't actually quite fit this format. Okay. So we've handled this mobile phone number. Does that go in there? So the question really would be, would you need to record students' historical mobile phone numbers? Okay, so you happy for me to put mobile phone in here? I just write about mobile. I might even write "ne" on the end of it, but okay, and okay. Right, now what are we going to do about sponsorship? Okay, so does sponsorship translate? Some, in the UK, and forgive my ignorance about the US education system, you can have sponsors, that so your employer might pay you to do a degree, you might get a scholarship to do a degree, you might get, there are ways of funding your education. Does that make sense? And this could be whatever. But so, for instance, I was very lucky. The army stupidly gave me money to attend university, a decision that both they and I regretted with a huge amount of regret. But anyway, so what about sponsors? So basically, the concept I'm having is some students may have a sponsor. So first of all, is the concept I'm trying to describe clear? Okay. Right. And what am I missing on that diagram before we go on to that? So what if I'm not quite yet?
Each address has to have one state.
Well, yeah, each address has to have a zip code. I think we could. Yeah, and we've got a state and a city. So yeah, I'm hoping there is no zip code that has more than one state, but let's pretend that there isn't. I'm sure that if you try really hard, you might be able to find a counter example for that. Okay, so sponsor. So sponsor name, sponsor contact, sponsor phone number. Are any of these functionally dependent on each other and not just on the primary key? So sponsor name is the Army. Sponsor contact, Colonel Withington Smythe. Phone number, +44, whatever it is, okay? So how are we going to handle sponsorship in this particular table? Am I going to put it in here? Fantastic. So what am I going to do? Make a new table called sponsor. Yeah? Okay. What am I going to have here? Sponsor name, yeah. Okay. Sponsor contact, yeah. Shall I have that? Might you have more than one contact for a sponsor? So but you can see how this is beginning to expand. So sponsor name, sponsor, you might have more than one phone number. Okay. So here's the next question is, so what sort of relationship do we have between student and sponsors? Yeah. So one organisation may sponsor many students, and one student, let's make it simple and say one student is only sponsored by one organisation, otherwise organisation, okay? So, sponsor name. So here's the thing, is sponsor name a good primary key for this table? No, why not?
Because there could be the army and the army in Britain, or I mean,
Yeah, then we could have the British Army, we could have the American Army, we could have whatever. We could have in the United States the National Guard. So it might not be unique. So what we'll probably do here is create our own field called sponsor ID. Yeah. Okay. But you can see we've now split our table into a number of different points. So, but is this quite right? Okay. Because do you remember what I talked about, sort of IDs that stand between fields? So we've got this table which has sponsors, but actually maybe it's not that our student has, our sponsor has many students, but maybe there is a sort of arrangement where presumably one organisation might have a number of different contacts, and that contact is relevant to an individual person, maybe? I mean, I don't know, but this is the point that, we need to find out. So we could have person contact. Sorry, I'm going to call this, it should be a noun, endowment, funding, something like that, okay? So I'm going to have another table here, and a organisation might have a number of funding episodes. The funding episode will have a student ID on it, yeah, so we know what student it's referring to, and what else? A sponsor ID, yeah. ID, it might have an amount, and it might have the person's contacts here. Now, the point here is that a very, very simple data structure that we had here, we might split into quite a few number of tables. Now, the advantage is when suddenly the sponsor changes their name, we change it once and only once here, and we guarantee it's changed across every single student address. Okay? We might well have a relationship between, why not, address line 1, address line 2, and we might have another address field here. But then you get into the sort of really horrible things about thinking, well, what is the exact relationship between a student and a funder? So basically, basically a student ID may be linked to a funding episode, which might be linked to a sponsor. One sponsor may sponsor many, many students, etc. We could have a horrible situation where a student might be sponsored by many organisations. But when you're designing databases, these are the sort of nightmare things that you have to try and consider. And basically it's trying to consider the really worst, the most strangest variation of that database. Yeah? Okay, question?
I understand that this seems to work, but I've actually been on the data collection end, and
Yeah.
people don't give you a lot of the information that you're looking for. So how would you,
Yeah.
Are you just kind of putting some null value in there?
And this is one of the issues that you have. So when you're designing a data collection unit, so if you're writing an Oracle database or whatever, you will have to make you will have to say what's mandatory, what's not mandatory. One of the things that's often really important, so physicians are really appalling at entering the correct data in our care. So in the UK, I'm sure American physicians are completely much, much better than this. We require them to write codes indicating what surgical procedure they did. And this affects reimbursement in their system. So one of the things we have to do here is to say, taps the screen and say, oh wait, you've forgotten this. But that can be a problem because people can have a workaround. But you're absolutely right. One of the real nightmares is to say, well, what can we do if a student doesn't give their social security number? Or presumably, like me, when I moved to the US and started here, I was an employee of Lango Health for about 2 months before I actually had a social security number. Because they take time to generate if you move to the US. So how do you handle that sort of problem? And these are sorts of things, which make real-life database design an absolute nightmare.
I understand where when you are, since you don't have an SSN, you can just put in a mock
Yeah,
That-
yes.
That makes sense, but if you're looking, for example, start date and end date of an address, people don't even necessarily remember how long they're in a house.
Yes.
How can you expect them to put down information that they may not even remember?
So the issue here is we're not interested in their entire address history. What we're interested in is presumably the start date when they enrolled and when they moved to another address, if indeed they did move to another address. So whilst this structure could be used to build the entire, their career history, we're really only interested in, while you're in employment. I mean, the question is it reasonable to assume that every student shares their address at the start? So when a student starts at NYU, is it reasonable to say, you will give us your address? Yeah, so that is pretty reasonable. So what we could say is we'll automatically populate the start date of the address with the date that you enrolled, because that's all we know. We don't know if you moved in there 50 years ago or 30 seconds ago. And the only thing we can do is put an end date in if a student bothers to tell us they've actually moved. Now, you're so right. Students do move, and they forget to tell their university they've moved, and then their graduation certificate goes to some completely random address or something like that. But yeah, you're right. I mean, handling missing data values in databases is a nightmare. You're so right. So you spend an awful lot of time trying to deal with this, and also putting in rules to try and say, you cannot create a student record unless you have an address, for instance. Okay, so we have 5 more minutes. So should we do one more example of this? Yes! Okay. So here's here is another example of a healthcare example. So I did the last one, you can do this one. So what do you think the first table is going to be called? Sorry? Patient. Yeah, that would seem a pretty good collection. All right. Okay. So we're going to have a patient table. So this is a table with patient in it. Okay. What are we going to have next in here? Name. Can I just get away with first name, last name? Accepting there are a whole heap of problems, and obviously patient ID. Yeah. And I'm going to have patient ID as the primary key, so I've underlined it. Okay. Admission date.
Should be admissions table or something.
Yep,
Admissions
absolutely,
students
spot on.
table.
So let's have a table called admission. I told you I was illiterate. That spells admission, by the way, in case you don't really believe my British spelling. Admission. So what might be an admission? So, yeah, patient ID, certainly. I'm just going to say patient ID because I'm lazy. Yeah. What else? Admission date. Yeah. What else? Discharge date. Okay. Now, here we have an interesting thing. What do we have as a primary key? Okay. So one thing we could do is say have patient ID and admission date taken together as the primary key. But what would be the problem with that?
They could go.
Sorry, go on.
They could go to the hospitals more than once on the same day.
Yes, they could. So this could be a real problem. We might be able to get with admission date or admission date time combined, or maybe we should create another unique key called admission ID. So when you're designing databases, you spend an inordinate amount of time trying to think of ways that this could admission ID. So I'm going to create a new field called admission ID, which is going to be a unique identifier. Okay, what's the relationship between patient and admission? Yeah, one patient might have many admissions. Presumably, we might have there may be patients who've never had an admission. Okay. Attending physician. How are we going to handle this? Yeah. So basically, the question is, does a patient? I'm really good on this. Get me into trouble. Does one patient have only one attending physician at any one time? So they have only one time, but for a stay, may they have more than one attending physician? And the answer is yes, they can in the US model of care. Okay. So over here, I'm going to have a table. So sorry, treading on you like that. So I'm going to have a table here, which is called attending, or sorry, which is called physician. Okay. Okay. So this physician presumably will have his phone number and various other attributes of him. I'm conscious we have 3 more minutes left to finish at 5:25 past. So will one patient have, one patient will have many physicians, maybe for their stay, and one physician will have many different actual patient admissions they're caring for at any one time. The easiest way to handle that is to create an entity that sits between them and says, I'm going to call this a care episode, okay, which I'm sure there's a US term. Does anyone know what it is? But in England, it would be called care consultant episode. I don't know. I'm sure there's a US name. Care episode. I'm sorry? Consult. Yeah, I guess it is. Yeah. Care episode. So basically, this care episode will have a patient ID. Sorry, will have an admission ID. So from the admission ID, we can track back and get the patient. Yeah. It will have a physician ID. What else should it have? Consult ID. Yeah. Well, yes, it should probably have its. Yeah, and you're probably right. Well, because. Yeah. So I mean, you're on exactly the right line. We probably will invent a new consult ID, a new identifier called consult ID. So I think that's a good point. Data consultation, maybe start date, end time, etc. And again, one physician will have many, many different care episodes. So again, you can see our very simple data structure. I'm not even going to get into drugs, but guess what? That's going to be in a different table. So the point is that you can see that this particular, even very, very simple data may be split into lots and lots of different tables. Now, okay, for next week's lecture, Thursday's lecture, isn't it? Yeah. We are actually going to do this in practice. I've got some data for you to download, which I assume I can put on GitHub.
Yeah, sure.
Yeah, great. So I will put that data on GitHub. I'll be really grateful if before next lecture, you could actually install the following. And if I actually show you what I hope will be working. Anyone managed to install MySQL on their computer? Great, fantastic. Point is to remember the ID. Okay. So the things that I think, if you just Google MySQL, you'll get to this website. And the thing I really would like you to do is to install MySQL Community Edition. This is the free open source version of the data. You have to register for it, but it is free. I have had no problem, and I don't know anyone else who has had any problems with this. From that, there are a couple of things I think you'll find really useful. One is the MySQL Community Server, which is the back end of the database itself. The next is MySQL Utilities. So this gives you a nice GUI front end to actually manage the database rather than trying to do it all through the command line, and we'll talk about that. And for next week's lecture, for those of you who are Pythonetic, the MySQL Workbench is quite useful, but what will be really useful is MySQL connectors, and download these guys. So this is from Tuesday next week's lecture. This is the glue that enables you to connect R to SQL Server, because presumably you're not wanting to be SQL developers, but you're wanting it to be able to use this in R. So one of the things in R you'll be doing is how, when you have a database like this, you can make it look in R like a single record of a type that you might use for a statistical analysis. Okay. So the time is now 26 minutes past. I was always told you should finish a lecture 5 minutes before the end of the time. I have overrun by 1 minute, which I apologise profusely. Thank you very much indeed.
All right. Thank you, Simon. It's excellent.
So which one should I download? Is it follow the link?
So you've got a Mac, haven't you? Okay. My suggestion is, yeah, for those of you with Macs, my suggestion is archive.